Flandoli from Pisa, and he'll talk about the effects of transport noise on PDEs.
Thank you very much to the organizers for the very pleasant conference and personally for the invitation to speak. I want to discuss essentially one result only, this theorem here. Let me explain the notation and assumptions. I want to consider this SPDE of transport type and linear. So it's a sort of one of the simplest model of SPDEs. I hope that the notation are not confusing, since it's necessary that you remember this equation. Let me rewrite also in this more compact form. So there is the vector field B with the gradient, and this noise is just one-dimensional Brownian motion, independent, multiplied by the partial derivatives of u. Sigma is just a real number. So sigma we can write in a sense a gradient of u times dw. And I use Stratonovich for more or less, okay, and I use the Stratonovich integration here. The assumption on the main point in the here is that the assumption on B must be very weak, otherwise the equation is easy, or at least classical. Cunita wrote did a lot of work on this kind of equations in the regular case. So the main point is that I will consider a vector field B deterministic, but very weak. Also this assumption, this will be rewritten several times, so I don't need to copy. This assumption is classical, we will describe in a second. And the result is that is a no blow-up result for the first derivative. So if the initial condition is differentiable in this weak sense, then the solution remains differentiable for all time. I forgot to write for every t. For every t, the solution remains differentiable. Unfortunately, I cannot delete the intersection, so I cannot write that W1R implies W1R. In the proof, I have a loss, and so the most elegant result in some sense is that the intersection goes into the intersection over all R. And unfortunately, I cannot take R equal infinite. Otherwise, the simplest, more elegant form would be that U0 Lipschitz implies U Lipschitz. But this is I cannot prove this result. So it's a result of no blow-up of derivative under very weak drift. And let me discuss several issues before the proof. First, the assumption. This condition is known in fluid dynamics as the Prodi-Serrin, or sometimes Ladizenskaya-Prodi-Serrin condition. The usual theorems look like that. If a solution of 3D Navier-Stokes satisfies, or for say any dimension, 3D Navier-Stokes satisfies this condition, then it is even more regular and is unique. It's a weak solution satisfied. This is unique, but it is open whether weak solutions satisfy this condition for 3D Navier-Stokes. And this condition appears in the stochastic literature for stochastic ordinary differential equation. Perhaps the first time in this paper, at least for me, this is the main reference. Krylov-Röckner. Under this assumption, they have proved pairwise uniqueness. Also some other results, but in particular, pairwise uniqueness is relevant, in my opinion, for what I'm talking about. There is a little difference that in the Prodi-Serrin condition. At the beginning, people proved only for less than 1, but then later for less or equal. And here, the proofs here, I work a lot on this equation too, but nobody found a way to reach the equal. But as you remember in the theorem that I want to prove, I can reach the equal.
There's no PDE, right?
Okay, the PD is in the proof, but not in the statement. The statement is that this SDE has a pathwise uniqueness. In the proof, one has to use an auxiliary Kolmogorov equation.
So the B is a different B than the one?
No, it's the same B. The B appears in the PD as, let's say, I mean, it's called drift as in both cases. In the PD appears here in the first order term and in the ODE here.
Couldn't one say that this is a characteristic?
Precisely.
Yeah.
These are the characteristics of this problem. So this, the late W, if you want a more classical setup, this is the characteristic curves of this problem. So the relation in the deterministic case under regular condition, also in the stochastic case, under regular vector fields, the relation is that ut of the solution starting from point x is equal to u0 starting u0 computed at x. So there is let me comment. The main remark is that the theorem I want to prove is not true in the deterministic case. So if we take a sigma 0 and we consider this equation under weak assumption on B, the theorem is not true. Essentially, below Lipschitz is not true. Below Lipschitz is not true. There are many counterexamples, but probably the simplest one is to take dimension 1, the usual square root, which helps to do a lot of examples, but with minus. And this equation develops shocks. If you start with a regular initial condition, there is a discontinuity at x equals 0 immediately. I wrote again the same relation, and this is a way to understand this result, that if the characteristics meet, due to this sinus minor, the characteristics meet in finite time, then from this identity you see that there must be a discontinuity. There is probably a picture here. These are the characteristics for this example that meet in finite time, and these are profiles, deterministic case, profiles of, we start with an initial condition which is smooth, they are arctangent, and immediately at any later time there is a discontinuity in the profile of the solution. This is the space profile at different times for the PD, and these are the characteristics. Let us see from the PDE viewpoint, in a sense, why the theorem fails in the deterministic case. Consider D equal 1 for simplicity of notation, essentially. So this is the PDE. The PDE, take the first derivative and call V. The first derivative satisfies this equation. The part here is exactly the same, transport part, but here there is derivative of B in dx. And if you try to apply several techniques, at the end you see that you need that this derivative is bounded. Essentially, you need the derivative of B in dx, this, let's say, potential coefficient here must be bounded in order to control this derivative. So below Lipschitz is very, very difficult to go in the deterministic case. And so you see that to reach in the stochastic case a B which is just of this form is a big improvement. It's not just a small technical improvement. The talk is on this no blow up, but it is more or less 5 years or more that we work on this kind of transport equations, but mainly in the past for uniqueness of weak solution, because there is a rich literature in the deterministic case on the uniqueness of weak solutions. So let me recall that the main result is the Perna-Lyons 98, in which B Lipschitz is generalized quite a lot. You see, it's just a W11 in space with a rather severe assumption on the divergence, perhaps. Under this condition, it's possible to prove that L infinity solutions are unique. There are extensions in the deterministic case, and we work a lot in the stochastic case to generalize this result. So I mentioned here 3 contributions. They work under different assumptions. It's a little bit long, so I don't write the assumptions. But just to remember that the problem of uniqueness of weak solution for the stochastic against, let's say, versus deterministic has been investigated a lot in the very last years. but we see that the effect of this transport noise on blow up is even stronger. I mean, I should write the assumption, but here is even stronger. I mean, because there is no deterministic result, but there is the stochastic result and a very weak assumption on B. And there are two proofs, essentially, of the theorem I stated in the first slide, two proofs. One proof goes through characteristics, and is the most natural, the first proof that was done in the last year, let's say, and now appeared on archive, is done by two groups. The analysis of characteristics done by these two groups is completely different. They use Malevin calculus, and we use a special transformation that I will show. But at the end, the application to the PDE is the same. And now I have a PDE proof, completely PDE proof of this result, and this will be the proof that I will show in the talk. So my talk essentially is on that theorem and the PDE proof that I give now. But before I give the PDE proof, let me recall something about the characteristics, which are very natural and one should remind. First, a remark. If instead of the LPB, you remember, I assume B of class LQ, LP, and so on. If instead of LQ, LP, we assume Hölder, this result of no blow up is a relatively easy consequence of this paper with Enrico Priola here and Gubinelli using stochastic flows. The result is even stronger, namely C1 goes in, also C1 alpha, for some alpha, goes alpha prime, let's say, goes into C1 alpha prime. So it's even stronger and relatively easy as a consequence of this paper. On the contrary, in the LP-LQ case is much more difficult. So,
Franco, when you write probability UT C1, you mean for all T, right?
For all T, sorry. I forgot everywhere to write for all T. I don't know why.
All T then is included in the set, or is it outside?
Inside.
Inside, maybe.
I have this, in fact, I have this estimate. The expected value, is outside. I can prove on the outside. I have this estimate that the derivative, the gradient of u at any power p in the x ds, I have both with the integral and with the supremo implies the integral. So the strongest is this one.
Then the zero set depends on T.
Yes, the zero set depends on T. You're right. Exactly. Okay. Let me remark that C1, I cannot reach C1 under this LP condition, except in dimension 1 there is a special result of Atanasio in which you can reach C1 under conditions which are weaker than Hölder, more related to something between BV and LP is weaker. So C1 maybe can be reached, but we don't know how in general. About the stochastic characteristics in the LP case, under the LP assumption on B, stochastic characteristics, essentially there are results which continue the research of Michael Röckner and Krylov, namely under this assumption with the strict minus, not only this equation as a unique solution pathwise, but also generates a stochastic flow of Hölder homeomorphism, Hölder of any order. And recently we have proved this additional result of W1R differentiability of this stochastic flow. The corollary is the main theorem, namely that if U0 is W1R, the solution remains W1R. So under this little bit more restrictive assumption, because I have to use this theory that I don't know how to generalize to the case equal 1. And the proof of those lemma is pathwise uniqueness, as I said, Krylov-Röckner. Existence of a continuous Hölder flow is in 2 papers by Fedrizzi and myself, and the differentiability is also done by this other group of authors at the same time. There is also a paper by these authors on the same subject. And a similar subject, let's say. It's not exactly a similar subject. And let me say just 2 words on the proof, but probably this is a mistake because I don't want to insist on flows. Just to mention that, which is the difficulty to prove that the flow is differentiable. That if you write you remember the equation for characteristics is dx equal to b plus sigma is just a real number in Wt. So if you differentiate in the initial condition, you get this equation for the derivative with respect to the initial condition. But of course, this requires a derivative of b, and we are assuming just LP condition on b. But there is a trick. There is a trick. One can rewrite the equation. One can rewrite first this equation in a special form, and then take the derivative. And the equation for the derivative then is meaningful. In order to do this, one has to introduce an auxiliary process, an auxiliary function, solution of this parabolic equation, which is much more regular than b. So even if b is only LP, the solution u is much more regular, and so all terms here have a meaning, and one can prove that this differential exists. We don't know, as I already remarked several times, we don't know how to prove that this differential is continuous or at least locally bounded, for instance. Let me show a picture which maybe helps to understand what happens for the characteristics. Without noise, the characteristics for this simple example, they meet immediately. With noise, apparently it seems that they meet, but in fact a blow up of the very last bits show that they don't meet, and the reason is that if you consider two of these curves, they approach exponentially fast, but the exponential degree of approach becomes infinite only at the origin. Outside the origin, the exponential approach is finite, large but finite, and this trajectory live around the origin in a certain sense in a negligible amount of time. It's a question of local time at the origin of this curve. So they spend a negligible amount of time near the origin, and so their exponential approach is still finite in some average sense, and they don't touch. So there is no collapse of the flow in the stochastic case. This is again the profile with a space blow up, the profile of the solution of the PDE. This is the deterministic profile with discontinuity, and this is how the profile looks in a numerical computation for the stochastic case. This transport noise is a sort of a random motion of the environment. You have a transport in an environment which shifts randomly, and so is not so the profile undergoes a sort of shift, random shift, and this singular point is moved with respect to the origin, and so there is no time for the profile to develop the discontinuity in some sense. It remains continuous, even if very steep. Let me go finally to the proof of the theorem by proof without a flow, made only by PDE estimates. And
stochastic characteristics, even in the deterministic case where they will never meet, when B is continuous, they should meet in the stochastic case, right, for two independent noises.
No, the noise is the same. When I'm talking about the stochastic flow, the stochastic flow has the same noise for different initial conditions, yes. Otherwise, you're completely right. Due to noise, they would meet even if they don't meet in the... yes, exactly. There is not the correlations phenomena due to noise. It's the same noise for different initial conditions. This is a work with Isabek. Is made of several steps. Oh, sorry. Is made of... push the wrong button. Is made of several steps. The first step is, as before, take the derivative in space. Let me say that this is what the proof given here is an a priori estimate. So I take the same equation with regular B. U is very regular due to results of Kunita, C infinity, even compact support, random compact support. If I take this initial condition with compact support, the solution is compact support, random, C infinity, and so I can do all derivatives on the solution. The point is that I will end up with estimates which are independent of the regularity of B. They just depend on the regularity of B, the LP regularity of B. So a priori estimate. So let me take the derivative of U and call VI. VI satisfies, as I showed before in the one-dimensional case, the same transport equation, but there is an additional term with V multiplied by the derivative of B, and we don't want these derivatives of B. Of course, this trick does not introduce any advantage with respect to the deterministic case. There is another computation which is typical, both deterministic or stochastic, namely for a transport equation you can take a composition by function. It's related to the renormalization theory of the Pernal ions, but here V is regular because we are working with regular functions, so V is regular. We can take the square. The square satisfies as the same structure here. I don't know why I pushed too many buttons. The same, very sorry. Now I'm back to the slide. The same structure here, and here there is V twice. There is the same term here multiplied by VI. No advantage with respect to the deterministic case. It's the same trick that one can play in the deterministic case. But this is the second step, and it is very important to do this step. Not only for the square, but for any power n. We have to do this step. The third step is stochastic. This is the first point in which we introduce the stochasticity. We move from Stratonovich to Ito. The proof, what I'm going to say, is probably not easy to follow in a talk. So maybe it's better that you just believe, if you want, you can see this, that Stratonovich goes into Ito, but the proof of what? That the correction is exactly the Laplacian. This is the point. One can check with some patient that the correction between Stratonovich and Ito is exactly the Laplacian. Some people know this very well in advance without looking at the proof. And so the equation for the square, but also the equation without the square, contains a Laplacian when you move to Ito. A Laplacian. This does not mean anything. It's equivalent to the original equation, and so since in the regular case, when B is regular, there is this property, this is a sort of reversible equation. I mean, there is doesn't mean that since there is a Laplacian, the solution is more regular than the initial condition. If you zero as a discontinuity, you see the same discontinuity in the solution. So there is no increase of regularity. This Laplacian is completely compensated by this Ito term. But the next step is to take the expected value. If we take the expected value in the previous equation, and of course we have to check that we have the martingale property for the Ito integral, for the expected value the Ito integral disappears. And so we end up with an equation that is really parabolic, a parabolic equation. And we will see after a few preliminary slides that this parabolicity is the main ingredient in order to relax the assumptions on B. But I don't show this immediately. First, I want to discuss in itself this trick of Stratonovich to Ito plus expectation, because it may look a miracle that you just play this and everything becomes parabolic. Unfortunately, it's not something that in any case gives us a great result. Sometimes it doesn't give really anything, this trick. So let me discuss this trick, Stratonovich to Ito, and then average in general, because it's a very interesting conceptual point. So let me write in a more abstract form the linear equation. It's the same equation as that, but you can think a more general problem, for instance, Schrödinger or any other problem, also a parabolic. A can contain a parabolic term, and rewrite in Ito form The correction is this one. And if we consider, for instance, this case, which is very relevant, skew symmetric B, this is true, for instance, for the first order operator there. They are skew symmetric in L2. Skew symmetric, then this B square becomes B star B, and B star B with the sign minus contributes to the ellipticity. In some sense, this operator is more elliptic than the original A. But there is still this Ito term, which in a sense compensate exactly this improved ellipticity. Let us see, for instance, that the additional ellipticity due to this term is compensated by the Ito term. How do we see that they compensate exactly? For instance, let me show a typical computation. We apply Ito formula to the square. There are details, but the point is that the correction of Ito formula is exactly equal to the good additional term. So they cancel out, and the Ito formula for the square ends up with the same A that we had at the beginning. No improvement of ellipticity, no improvement of stability, for instance, also. So there is so this is a fake improvement of ellipticity. But of course, if we take the average, if in this equation we take the average, and if we can take the average and say that this is 0, we end up with a deterministic equation in which the ellipticity is improved. So the question is, this couple of tricks together, Stratonovich, Ito, and then average, is always useful. For instance, I can show this simple example for this equation at the pathwise level. Without average, there is no improvement of regularity. With the average, there is a huge improvement of regularity. This function becomes infinity with the average, even if U0 is very poor. So the point, the fact that this equation for the average is very regular, is a parabolic equation, corresponds in this example to the fact that this is infinity, but this has no influence on the pathwise property without average. So we cannot deduce any pathwise property from the increased ellipticity of this problem. So this general trick does not always pay, even in the linear case. Let me remind a classical result, which I find very intriguing, from Arnold, Crowell, Wistutz. They considered exactly the equation I wrote before in finite dimensions with a skew symmetric B. They considered the top Lyapunov exponent, namely the top, you have to you analyze the exponential stability, and this is the best, the top exponent for the exponential stability. And they proved that if you increase the noise, you can, they proved that you can find operators B such that if you increase the intensity of the noise, you reach trace of A over D. This means that even if we start with A, which has some positive eigenvalue, so some exponential blow up, if there are sufficiently negative eigenvalues so that the trace is negative, the system becomes stable, pathwise. I didn't write, this is a pathwise result. It's a stochastic system, so this is pure Moshut. So there is so it's really true that this improves the stability. So on a side, this result is a result in which this kind of noise improves the property in a sense of improved ellipticity. So it's a positive result. On the other side, it improves only to a certain degree. If we take the average, using very easy B, we can stabilize as much as we want. But we just stabilize the average. We don't stabilize the trajectories. And so this is also, again, to say that this trick of Stratonovich Ito plus expected value it's not said that it really means something. It depends. With very difficult proof, maybe one can prove that there is a regularization, but it doesn't follow simply from the average. So now let me go back to our PDE, to the transport PDE, and we see why the squares. Why the squares? Because with the squares, we have a parabolic equation for the average. If from this parabolic equation I can deduce, for instance, this estimate, or with other powers, from this estimate I have an estimate of that form. And then I have a regularity result. If I don't take the square, here, I have the same parabolic equation for W, but without the square. And then I get that the expected value of this derivative is very regular, but this has no consequence, no information on U from this. Remember that U is infinity, because I'm working in the philosophy of a priori estimates. So I already know that U is differentiable. The point is which estimates I get on U from this. No estimates on U from this. And so it's very essential to take the square in one of the steps above, the square or the n power. In the one-dimensional case, the proof can be completed quite easily, because you remember, perhaps I can show the previous slide, sorry if I change. You remember that in this equation there is the expected value of Vi Vk, unfortunately. If we study Vi square or Vi power n, here we have Vi Vk. And so this is not a closed equation for Wi. But in dimension 1, it is a closed equation. So in dimension 1, this is the expected value of V square. So the equation for W is closed. Still there is the derivative of B in the x, but it's sufficient to analyze the regularity by means of energy estimate, because then if you do the usual energy estimate, the derivative of B in the x can be transferred to W. And W accepts derivative, because there is this coercive term here. For sigma equals 0, this term is not present, and so we cannot handle this derivative of W, but here we have derivative of W. And so now the point, so this term with dB in the x becomes of this form, which is exactly the same form of another term which already existed. So the only point now is to estimate this term with respect to this 2, and it is just here that for the first time comes out the Ladyshenskaya-Prodi-Serrin condition, because the point is that this term can be estimated by the first derivative with a small coefficient plus this term, and then you use Gromwall. By the way, this kind of computation are exactly those done for 3D Navier-Stokes. So, and before this proof, there was this analogy that the Ladyshenskaya-Prodi-Serrin condition appeared in the stochastic work of Krylov-Röckner and in fluid dynamics, and I couldn't say exactly where it plays the same role. Here is exactly the same. Since we are doing a completely PDE proof, we end up exactly with this term. If in Navier-Stokes, this B is U. In Navier-Stokes, if is U, I mean, you have not to think to estimates on U, because if you take just U, is 0, the term is 0. But if you want to prove uniqueness for Navier-Stokes, you take two solutions, take the difference, and write the equation for the difference. There is a nonlinear term of that form in which appears U1 and U2, so it doesn't cancel out. U1 and U2, but essentially the point is that this B is like the solution, W is again the solution, W is again the solution, but maybe different solutions. And so one has to estimate exactly this term in Navier-Stokes. You do this estimate under the Ladyshenskaya-Prodi-Serrin assumption. And so the parallel now is completely completely trivial between these two theories. And then I said, by Gromwell, you close the estimate. In the multidimensional case, we need more steps because, as I remarked, there is VI, VK, and so this equation is not closed. If we apply energy estimate, we end up here, and when we put the derivative on this, we have the derivative of this product, and we don't know anything for the derivative of this product. And so the point is that we have to introduce the equation satisfied by these expected values of the product. So there is an additional step, a logical step, which is we have to introduce, if we call Vi the space derivative of U, we have to introduce all possible products of Vi, because we have to reach power n. It's not sufficient to reach power 2. We have to introduce all possible products and write the equation satisfied by this product. But the SPD satisfied by these products have the same structure. The transport structure is preserved, and there is some term on the right-hand side, the same structure. Then take expected value, and this expected value satisfy the parabolic equation. I have got to the end. So for this expected value, we do the estimate, and from the estimate, we prove the theorem. Let me just mention two concluding remarks. This new proof has some advantage, of course also disadvantages, but the two advantages is, one is this less or equal, which is elegant in my opinion. But the other is that it's easy to iterate this proof to higher order derivatives. So if we assume that the drift has derivative in this class, then we can go to W2 spaces. And I suspect more, but the proof becomes very heavy because you have seen we had to introduce these products for the first derivative. For the second derivative, there are more, and so on. So I stopped my computation to the second derivative, but the principle is clear that if the derivatives of B satisfy Prodi-Serring, then the solution preserves the corresponding regularity. And notice that at the level of 2, this is still weaker than Lipschitz. This assumption is still weaker than Lipschitz. So deterministic, only Lipschitz. Stochastic, weaker than Lipschitz, we can reach a second derivative. And other remarks, there is a main open problem that is nonlinear and also random drift. If the drift is not deterministic, we don't know what to do. I want to mention this paper. The technique is completely different, but there is some parallel philosophy. They study a linear Schrödinger equation with multiplicative noise in the form of Stratonovich. In some sense behind there is the passage between Stratonovich and Ito and so on. They prove strongest Ricker, Arnaud Debussy and Tsutsumi. They prove strongest Ricker estimates, and using this stronger estimate for the linear problem, they can improve the no blow-up theory for semi-linear case. Very interesting work. And let me finally mention that using this result with Gubinelli and Maurelli, we have consequences on the uniqueness of weak solution, which are very strong, and also the uniqueness of stochastic Lagrangian flow. But this is a little bit technical. I just want to mention that. Thank you very much.
We have lots of time for discussion. So,
I mean, it seemed kind of that there is, in a way, a commutativity behind it, because when you were briefly alluding to the proof for the which uses the pass, you were writing down the integral in order to prove the differentiability of phi. You were writing down actually the integral for the expected value with respect to omega, right? I mean the Fokker-Planck equation for one characteristic.
Yes.
I mean, so there seems to be a kind of a commutativity when you look at all the I mean the space omega of the noise and the space of somehow of your function. So looks a little bit like taking a particular slice in this huge space.
What you say is perfect, except that I don't take the commutativity. What you mean by commutativity is...
Well, I mean that you can, if you take the expectation
yes.
of your
Yes.
yeah, you could in a way because of the linear structure at one time shift this to the to something which is connected with the Kolmogorov equation for the characteristic. Yeah.
Thank you for the interpretation.
Maybe just I wanted to focus on one particular aspect concerning the behavior of the expectation. Once you have the equation with a Stratonovich part and you take the expectation and you see that you have a relatively regular behavior of
yes.
expectation. So I had the impression, just the feeling that if instead of having Brownian motion, one has fractional Brownian motion or some Gaussian process, so that you interpret the Stratonovich integral as you have a Skorokhod integral plus a trace term, I have the impression that the behavior would be similar. In the sense because the type of correction that you have is, for instance, if you integrate a function of the process, you have a correction of type f prime and so on, like this. And maybe one could have some similar phenomena in that case. Because the Skorokhod integral has expectation 0 and it plays the role of a martingale in some sense, and the correcting there could be maybe similar. So I mean, maybe this phenomena is maybe a little bit more general than for classical calculus.
It's very interesting remark. I cannot say anything on this remark, which is very interesting, but it relates to a problem that I cannot solve, namely the case when, also related to your question yesterday about if one takes smooth approximation of the noise, all these techniques is destroyed because there is no more Laplacian, but it's very strange that the result is not true. So fractional noise could be in some sense. I don't know.
All right. If there are no more questions or comments, let's thank the speaker again.
Thank you.